Hello again everyone, welcome back to ptet.chemistry channel. In this tutorial video, I'll cover these topical MCQs, the section B topical MCQs, which involve 3 statements or 3 options, where if 1, 2 and 3 are relevant to what they're asking, they'll give you option A, B will be 1 and 2, C will be 2 and 3, and D will be just option 1, relevant to whatever they're asking. So what we are going to do always is to check for option 2 based on this logic. Okay, so in this first question here, it's saying that why does this mixture of H2 and Br2, why do they react faster, okay, at a higher temperature? So we know that in the theory paper, when you talk about why rate increases as temperature increases, you talk about collision frequency, which is higher at higher temperature. But in A-level chemistry, you also start to learn about Maxwell Boltzmann distribution diagram, where we have energy on the x-axis and we have distribution of molecules, so the number of molecules with energy E. So if there is at 400 Kelvin, then what I would draw at 500 Kelvin is, that's probably not the best one. At 500 Kelvin, my graph will skew to the right, okay? While my total area under the graph remains the same because I haven't changed the number of molecules, the total number of molecules, and I will have activation energy of the reaction. At a higher temperature, I increase the proportion of molecules having energy E, and therefore I will have more molecules that have sufficient energy to react, therefore I have faster rate of reaction. That is the second additional factor. In addition to collision frequency that you normally talk about from your O-level or your IGCSE or your GCSE years, yeah? So colliding more frequently is correct at a higher temperature, but we also talked just now about the higher proportion of effective collision as a result of this shift in Maxwell-Boltzmann distribution. But this bit, the activation energy is lower at higher temperature. That is incorrect because when you change temperature, your original activation energy is still there, and only catalyst can give you a new, lower activation energy, only with a use of a catalyst, not a change in temperature. So that's option B. This next question is so you have 10 cm cube of this 0.100 mole per dm cube sulfuric acid, and then you use the same volume and the same concentration, but you use ethanoic acid. So I have a feeling that this is a strong versus weak acid. Strong versus weak acid. And the fact that you add 1 gram of magnesium. Magnesium is in excess. Therefore, the acid is limiting. Okay, acid is limiting. Temperature is the same, so that is the control variable. Okay, if you have done practical chemistry before, in fact there's something that you will have done definitely in your A-level time, you will know what is control variable. It's something that could affect the rate of reaction, but in this case I'm not investigating temperature, I'm investigating the different acid. Okay, so strong versus the weak acid. So I need to maintain this variable. I need to make sure they are the same. So that's our control variable being kept constant. Neither reaction is complete after 2 minutes, but both are complete after 20 minutes. Alright, so even though the concentration in mole per dm cube of the strong acid and the concentration of the weak acid is the same, alright, so why don't we think about stoichiometry? If you write a balance equation, magnesium plus sulfuric acid will give you magnesium sulfate plus hydrogen gas. If you have magnesium plus ethanoic acid, this is not new because you will have done this in your O-level, GCSE or IGCSE chemistry. Okay, you will have seen the charges are not balanced because this is -1, this is 2 plus, so this is where you need to do your lowest common multiple. You have 1 and you have 2, therefore your LCM is going to be 2. You need 2 of these. Alright, so I like to put my charges in so that I can see how they balance out, but you can also write them in such a way that MgCH3CO2 like that, twice, it's perfectly fine like this. It's perfectly fine like this. I just find that I don't make mistake when I can see exactly what is going on. And people make mistake when they cannot see what is going on, because you need 2 of that. So you need 2 of these, and that will give you the H2 there because of the 2H plus. Both of these are what you will call redox reaction. So these are metal plus acid reaction. They are classified as redox because the acid, the H plus 1, become hydrogen 0. So there is your reduction. Okay, the magnesium 0 become magnesium 2 plus. There's your oxidation. These are classified as redox reaction. So what do we know? The magnesium is in excess. The acid is limiting. The acid is limiting. So I should probably work out the mole of the acid. All right. As you can see, they have the same volume and the same concentration for both the acid, but here the stoichiometry is not the same. Therefore, they are not going to give me, hang on, let me think. Okay, the stoichiometry is different here, all right? So the mole of sulfuric acid is to the mole of H2, for example. Okay, that is 1:1. Sulfuric acid and H2, 1:1. So I have 10 cm cube, 0.100 mole per dm cube. 10 cm cube convert to dm cube times 0.100 mole per dm cube. I want to know what is the volume. I want to know the volume of the gas. So I should use volume of H2. I will divide that by 24 dm cube. Yeah, it doesn't matter. It's a room temperature and pressure, I think. Room temperature and pressure. They don't say, but I will assume room temperature and pressure. Therefore, the molar volume of a gas is 24 dm cube per mole. Or of course, you can use 24,000 cm cube per mole, both of which would have been alright. Depending on how big is the value. I have a feeling that 24,000 will give me a better value. Because of the very small number on top. As you can see, very small and very small. So I use 24,000. That means my volume of hydrogen will be in cm cube because I use cm cube per mole. So bring all of this up, leave all of this here, and then bring the 24,000 up. So that's 10 times 10 minus 3.100 times 24,000. If you are unfamiliar with this fraction method of doing mole calculations, feel free to watch my other tutorial videos on mole calculations and stoichiometry, alright? So you can see more examples. So that much sulfuric acid will give me 24 cm cube of hydrogen because these are the actual reacting ratio of the H2SO4. These are the actual hydrogen produced based on how much they reacted. These are from the balance equation which you have written. Of course, balance equation, right? Now the mole of the ethanoic acid. So this question suddenly seems very long because I have spent more time talking about it rather than just jump straight into the answer, yeah? So 2 mole of the acid give me 1 mole of the H2. 2 mole of the acid give me 1 mole of the H2. Remember just now it was the same volume and the same concentration. Same concentration, same volume. So it was 10 times 10 minus 3 times 0.100. Again, the volume of H2 over 24,000. So I'm not gonna do the whole thing all over again, but essentially it's 10 times. No, actually maybe I'll do it because this is different, right? So I will move the 2 down and then I'll move the 24,000 up there. Move all of this up there, move the 2 down there, let's divide by 2. And then bring out the 24,000 as times 24,000. If you have problem rearranging this equation, you should probably do it in 2 steps, and eventually over time you gotta improve and be able to see what is going on, yeah? So that volume will be in cm cube because I've used this divided by 24,000 cm cube per mole, which is the molar volume of the gas at room temperature and pressure, which I have assumed, alright? Anyway, so neither reaction is complete after 2 minutes. So we know 2 things. We know in terms of stoichiometry, when the acid is limiting, the sulfuric acid will give me more gas than the ethanoic acid at the end of the reaction. Alright? But I also know strong acid versus weak acid. So the strong acid will have produced more gas because it is about faster reaction. This is about faster for the strong acid, which does not partially dissociate but fully dissociate into H+, so you will get a faster rate. After 2 minutes, neither reaction is complete, so 2 is correct. After 2 minutes, the sulfuric acid is at a higher temperature than ethanoic acid. So we know that this reaction produces hydrogen, and you have done a calorimetry. This is topic 7. You have done topic 5, calorimetry, where you just pour this into this and then you measure the temperature rise, because you have done the experiment before. There's no way you could have done A-level chemistry without having done calorimetry. Alright, so these two reactions, metal plus acid, these are exotomic reactions. Because the reaction with the sulfuric acid is faster, okay, that means you would have a faster rise in temperature as well compared to the ethanoic acid, which will react a bit slower. Alright, number 3 is to do with stoichiometry. That was what I have done. With all these calculations, is to show you that the sulfuric acid, because it is limiting, because they specifically said the magnesium is in excess, so the acid is limiting and the equation is not the same, and you will get more hydrogen gas with sulfuric acid than ethanoic acid at the end. So the sulfuric acid produces more gas than ethanoic acid after 20 minutes because that is complete. If you read the question, complete after 20 minutes. So all 3 are correct. But I am just not sure that some students have gotten this correct without really understanding the stoichiometry. They just think about rate without thinking about the stoichiometry at all when the reaction is complete. Alright, and it's a different story. It's a different story if they remove this one. If they say the magnesium is completely used up, so the magnesium become limiting, then it's a different story. That means it doesn't matter whether you use sulfuric acid or ethanoic acid, you'll get the same gas. Very easy for Cambridge to change the question, yeah? So gotta think carefully about what you have read. Spend a bit long on that question, so let's speed up a little bit. You have catalytic converter. It remove harmful stuff, so it remove things like nitrogen oxide. You want to have lower exhaust concentration of nitrogen oxide, so you want to have lower pollutants. If you make the exhaust gas flow faster, you know how it's like a honeycomb structure? So inside a catalytic converter, you have like honeycomb structure. I can't draw honeycomb very well, but imagine that you have honeycomb structure where you have increased surface area already. Okay, so these are engineering design. If you're into engineering kind of thing, you will have known about this kind of modification. So 1 I can tell is definitely correct. As a result of this honeycomb structure, we really want the increase in surface area. These things enter as gases and they go out as cleaner gases. So harmful pollutants, things you don't want to just go into the atmosphere, and I say cleaner product, okay? So what happened in reality is that these come as gases. These are solids because they are rhodium, palladium, platinum, precious metals. These are your heterogeneous catalysts, which are part of the definition under topic 7, which is rate reaction or reaction kinetics. You need to know the definition of heterogeneous catalyst. If you make the gas flow faster, they will have less opportunity to stick onto the surface of this solid catalyst. If they can't stick onto the surface of the solid catalyst, they can't react, and therefore they can't be catalyzed, and therefore you will still not get clean product out of it. So you don't want it to be faster, you want it to flow slower so that they have more time to stick to the surface. The reason is because a lot of them would have filled up the surface at the very beginning, but if you leave them longer, meaning to say they flow slower, they will have more opportunity to stick onto the surface. Once the reaction is complete, the product will leave the surface, and then it will leave some empty catalytic sites for your oxide nitrogen to stick on the surface and then start reacting again. Okay, so 2 is definitely incorrect. You want it to be slower. Alright, so there's option D. And you definitely do not want higher temperature of combustion, because higher temperature of combustion will mean you produce more nitrogen oxides. So the more you produce, but you still have the same catalytic converter, the more oxide nitrogen produced, they're going to be overwhelmed, okay, because they can't process so many at one time. So some of the oxide nitrogen are going to escape, and that will increase the concentration of nitrogen oxide in the exhaust. In this next question, so we have this carbonate plus acid reaction. Carbonate plus acid reaction, and you measure the rate of reaction. You have 100 cm of distilled water added to a second portion of the acid. So you are diluting the acid. When you dilute the acid, the concentration of acid decreases. So when we talk about concentration, when we change concentration, okay, we change the rate of reaction due to the collision frequency. All right, so one is definitely correct. You reduce the collision frequency. The rate is also slower, but you are not changing the proportion of effective collision at all, because when you do dilution, you do not change the average energy. Okay, so dilution does not change the average energy of your reacting molecules, because they do not affect or change your Maxwell Boltzmann distribution of energy. Same thing with changing pressure. They can change your collision frequency, but they do not affect your Maxwell-Boltzmann distribution of energy of your reacting molecules. So you still get the same proportion effective collision. It's just that collision frequency has changed. This question is about acid dilution, which is to do with concentration, but it's the same deal when you talk about pressure changes as well. Okay, so 2 and also 3 are incorrect, leaving you only option 1 as the only correct answer. Okay, this is the last question of this 5-question series on reaction kinetics, rate of reaction. So again, you see, just as I mentioned just now, we talk about increasing or decreasing concentration. Previous question was about dilution. So there was decreasing concentration. We do not change the Maxwell-Boltzmann distribution when we change concentration or pressure. Okay, so in this case, it's about changing pressure. Changing pressure can increase the rate of reaction when temperature is not changing. So again, that is not changing the energy distribution of your reacting molecule. So it's not changing your Maxwell-Boltzmann distribution of energy for your reacting molecules. So more molecules have energy greater than activation energy at a higher pressure. This is to do with proportion of effective collision. And based on what I just said, because you do not change the Maxwell-Boltzmann distributions, therefore you do not change the proportion of effective collisions. Alright, since you do not change the proportion of effective collisions, 2 is wrong, and we know 1 is correct because it's about collision frequency. Just like in the previous question, changing concentration, changing pressure only affects collision frequency. Therefore, only D is correct. That means only option 1 is correct. And that's the end of this 5-question tutorial series. And thank you for watching, and thank you for sharing the channel with your friends, your class group chat, and various other people whom you think the channel can benefit. Alright, so see you in the next video.